very brief historical note, which is that these bursts were discovered a long time ago. And for 20 years or so, we didn't know something very basic, such as how far they are from us.
Is that an atlas?
Vela. Sorry.
Vela satellite.
Vela. Yeah, Atlas. The information about how far they are really started coming more than 20 years after the discovery of gamma ray bursts, and that was Compton GRO Observatory, launched in 1991. It established two things, one of which is that these bursts are isotropically distributed, and moreover, they have a distribution in space which is non-Euclidean. And that implied, the two together, that they are at large distances, at cosmological distances. So this is showing more than 2,000 gamma ray bursts discovered by Compton GRO battery satellite. Each circle, each point that you see is a gamma ray burst. Color coding is for their fluence, and the distribution is isotropic, with no, for instance, preference for the galactic plane. So that, together with the space distribution being non-Euclidean, convinced most people, but not everyone, that gamma ray bursts are coming from located at cosmological distances. The firm proof of that had to wait a little longer. Babosag satellite, which was launched in 1906, it's Italian-Dutch satellite, and that localized burst to about 5 arc-minute, which was a factor of 20 improvement over Compton GRO battery localization, which in turn led to the discovery of optical afterglow and measurement of redshift, and established for sure that these explosions are typically at a redshift of 1 or so. And that in turn meant that the amount of energy release, if these explosions are isotropic, is order of 10 to the power 53 erg. We know that at least some fraction of these bursts, the so-called long duration gamma ray bursts, meaning lasting for more than a few seconds, are produced in collapse of a massive star. And this is the evidence, or at least one of the evidence we have, looking at the spectrum, for instance, at different times after the gamma ray detection, gamma ray trigger. The spectrum of gamma ray burst is shown in solid line, and for comparison, a spectrum of a supernova, a particularly energetic supernova of type 1a or type 1c, shown here in the dotted light curve. You can see the similarity for yourself, and most of you have seen this before. It's for this particular part, the first 6 slides certainly are to give you a framework. Those of you who are new to the field, particularly the students, have an overview of what the major properties are of gamma ray burst. So this similarity shows that gamma ray bursts are associated, long duration gamma ray bursts are associated with core collapse, and furthermore, the long duration gamma ray bursts are also seen invariably associated with the star forming galaxies. So that's another evidence that you're looking at explosions which have something to do with young stellar population. On the other hand, if you look at the host galaxies of the short duration gamma ray burst, which means bursts that last for less than about 2 seconds, then their host galaxies are of all different kinds. There is no particular preference per se that they would occur in star forming galaxies. They occur, some fraction of them, although it turns out that it's a small fraction of them, about 15% or so of short duration gamma ray bursts go off in elliptical galaxies. So at least some fraction of the short duration gamma ray bursts are associated not with young massive stars, but old stellar population, implication being that they are likely to be associated with a binary system, most likely neutron star black hole or neutron star binary system. So that's the short duration, at least fraction of the short duration gamma ray bursts have origin in old stellar population. The thing that separates gamma ray burst from supernovae is that in gamma ray burst, the material that is ejected is moving close to the speed of light with a Lorentz factor of 100 or so, 100 maybe even larger. And there are many, many lines of evidence and many, many lines of theoretical argument, but the best one is shown here. It's the most direct evidence that you are looking at explosion where material is moving close to the speed of light is shown here. What you're looking at here is the size of the remnant. This is for a particular gamma ray burst that went off March 29th of 2003. It was a relatively speaking nearby gamma ray burst at a redshift of 0.17, a distance of a mere 530 megaparsec. And what you are looking at here is a VLBI measurement of the size of the remnant as a function of time. X-axis is being time after the burst in days, and the y-axis is the angular size of the remnant. And what you have here is that the remnant appears to be expanding at a speed which is larger than the speed of light. 25 days after the explosion, it was expanding at a speed of 5 times the speed of light. And even, for instance, at about 70 days after the explosion, the remnant appears to be, the keyword is appears to be, expanding at a speed which is 3 times the speed of light. So this superluminal expansion is a telltale signature, telltale sign that you are looking at something which is moving at very close to the speed of light. You can translate that immediately to the Lorentz factor of the expansion, and it is 7. Lorentz factor is about 7, 3 weeks after the explosion. You can extrapolate it back in time and comes out to be something on the order of 100 or so is the Lorentz factor at the time of the explosion or soon after the explosion.
This is adiabatic. It's slowing down.
It is correct. Adiabatic in the sense that it's sweeping up material in the surrounding medium and slowing down.
It's just losing energy.
Exactly right. It's losing energy to the surrounding medium, but not to radiation as such. It's simply being shared by larger and larger amount of gas mass. By the way, I should have said at the very beginning, keeping in the spirit of the workshop, I would very much like to be interrupted even continuously and ask questions as they come to your mind instead of forgetting about it later on. Other piece of information that we have, which seems fairly well established, is that these explosions, gamma ray bursts, as opposed to supernovae, are highly beamed. And the evidence that we have comes from afterglow, particularly historically from the optical afterglow. And what you're looking at, whole bunch of bursts, they were detected by babosacs. The left panel showing the radio light curve, the middle optical, this right panel, the X-ray light curve. And what you see in the light curve, is there a pointer by any chance? Not that it's particularly crucial, but if there was a pointer, it is easy to kind of point and guide your.
Maybe on the remote control there is a light laser or something.
So for instance, let's look at this light curve here. Optical light curve, it was falling off with a certain slope, and then it is steepened. The fall off of the light curve or the flux is steepened. That break is a signature of a finite size of the jet. If you don't know why, you can always ask me. I'm not going to explain for now because I'm going to go on and to other data and other physics, but that's the signature of a finite jet size. And from that, one can measure the opening angle of the jet, and it turns out to be, it varies from burst to burst. It could be as small as a few degrees for some bursts, or as large as 30, 40 degrees. Basically, at that point, you lose the ability to be able to tell how wide is the jet. Which means that you can correct for this finite jet opening angle and determine the true amount of energy release. Remember that isotropic energy was something on the order of 10 to the 53 erg. You correct for the fact that the energy is coming out in a jet of a finite opening angle, the energy comes down, and it becomes something closer to 10 to the 51 erg. That's roughly the energy. Again, it varies from burst to burst. But there is a clustering of energy, meaning many more bursts have energy order of 10 to the 51 erg, which is supernova energy. But that's coming out in relativistic outflow. Swift launch, that was another major led to a number of interesting and important discoveries. Swift launch, and 2 years ago, prior to that was Integral that was launched. What Swift found is that there is a complicated behavior. There was a gap in the data prior to Swift, a gap of almost 7-hour gap between the gamma ray burst and follow-up afterglow observation. That gap was filled or largely filled by the Swift satellite. It could slew quickly on a time scale of less than a minute and point the X-ray telescope in the direction of gamma ray burst and also UV optical telescope. What Swift found is that the X-ray flux undergoes a very rapid decline at the end of gamma ray burst. So for instance, here is an example, gamma ray burst, so-called prompt emission lasting for, in this case, 20 seconds, followed by that a very sharp decline in the X-ray flux falling down as 1 over T cubed or maybe even faster than that. That lasts for a few minutes, and then it is followed by flux declining not so fast at all. It's almost a plateau. That lasts for almost an hour. So these were unexpected behavior, and this steep decline, for instance, certainly tells us that whatever is the central engine, be it a black hole, be it a neutron star or a magnetar, to be more precise, is turning off its activity. That activity is declining rapidly in time. That's what this is telling us. So this is telling us something about the central engine. And if you believe that the central engine is a black hole, which is accreting matter from the surrounding, outer part of the star, then you can invert this behavior. This light curve can be inverted to learn something about the progenitor star property. And that's shown here in the next slide. This is showing simply schematic behavior in 3 different colors, prompt gamma ray, this rapid phase of decline of the X-ray, and followed by a plateau in the X-ray band. And that in turn is converted to the property of the progenitor star that collapsed and gave rise to the gamma ray burst. So the prompt emission is a result of collapse of the core of the star, the size of which is something on the order of, 10% of the solar radius. Collapse produced the prompt gamma ray. The surrounding envelope surrounding the core subsequently was accreted by the black hole that gave rise to this rapidly declining X-ray, and then the plateau where material from the outer part of the star was accreted on a longer time scale of minutes to an hour, leading to this plateau that we see. So it can be, but keep in mind that this is based on a model that what was produced in the collapse is a black hole, not a neutron star, because the story would be different. If it were to be a neutron star, magnetar, then this inversion is first of all more difficult, and also it would be a different kind of inversion. Please go ahead.
Since you asked for questions.
Please do. Yes, that's great.
In addition to this neutron star black hole divergence, you also assume that the emission that you observe is produced at the same physical location.
It need not be at the, very good, very good. It need not be produced at the same location where the gamma ray is produced, but yes, it should be produced somewhere within the jet, within the outflow, as opposed to, for instance, in the surrounding medium. So that is certainly assumed, correct, in the inversion. Otherwise, the inversion is not going to tell us about the central engine. That is a very good, that is to say, I'm glad not only that you asked the question, but I'm glad for, this clarification. Yes, please, go ahead.
There's got to be a problem with associating the prompt emission time with the radius of the core, since there are bursts that literally last hours.
There are very few bursts that last for half an hour. Very, very rare. The distribution, if you see, there is a peak at about 10, 20 seconds, and then there's a fall off. Yes, there are bursts which can last, and I will show you one example of it, for 200 seconds, 225 seconds. But those are rare. However, the point being, you're saying that what about those bursts that do last for much longer time? So let me interpret your question that way. Yes, something could be going on. It could be that the core collapsed on a short time scale, produced a flash lasting for maybe 10 seconds, 20 seconds, 30 seconds, but the outer part continued to be accreted, had the right property of the angular momentum, for instance, in the outer part, that the activity kind of got extended. So those cases could continue to follow this accretion history. I see nothing in principle that speaks against this possibility. Now I'm trying to see what maybe you are thinking, and I'm not sure, so you may have to just say what is it, what thought is going through your mind, and then I will try to clarify and answer that.
Doesn't the prompt emission, isn't the physics we extract from a prompt emission
Yes.
really in the individual pulsations? Basically, the question.
There's no pulsation. See, it's black hole, right? So there's no, no, please, go ahead. Please go ahead.
So the black hole will be in a highly excited state and will actually pump.
It could.
It'll have oscillations from that.
But that quickly dies down.
The question that I had is your rapid fall off.
Yes.
That is much longer time scale than the natural X-ray cooling, so that you're forced to be pumping energy up by accretion.
It is correct. That is exactly correct.
Right.
It is pumping energy.
And
Correct.
the 3 times 10 centimeters is well outside of the usual zone of instability.
Correct.
Right. But you're assuming when the black hole form, the outer shell is getting blown out.
It can. Part of it will be. Very
Right.
true.
And then this inner 3 times 10 centimeters, you're assuming is chaotic, and therefore some of it will get pulled towards the black hole.
It will be pulled toward and will be accreted.
Right.
Some fraction of that will be accreted. That's correct.
And so in your model, you're saying, I rule out simple cooling, I rule out anything. What I need is some of the outside to be blowing away.
Correct.
I need for a bit to
That's
stay
correct.
behind. And somehow you have to form an accretion disk in order to get this signal out. Right?
Very correct. But when the material is falling, if the material is bound, correct, as opposed to being unbound by the energy coming out from this accretion, the prior episode of accretion, as long as it is bound, it is going to form an accretion disk, provided that it has got sufficient angular momentum. If it has got sufficient angular momentum, which means, to be precise, the specific angular momentum per unit mass should exceed the specific angular momentum of the last stable orbit around the black hole. If it exceeds that, it is going to be hung up, which means it's not going to fall directly into the black hole. It is going to form an accretion disk, and then accretion will proceed. And that's how
But
this.
if it doesn't do that, you're not going to get that.
Absolutely correct.
Right.
That's absolutely correct. If you do not have that, if you have this thing, then in that case, disappears. The material, the accretion.
It actually snuffs it out.
Correct.
Because it's non-transparent. Right?
Correct. So that's.
So you're having to assume an accretion disk forms.
No, I am assuming that accretion disk forms. Sorry, go ahead. So yes, there is an accretion disk form, and the property is controlled by how rapid is the rotation. So for instance, here, the rotation rate information, which is actually provided here for the outer part on the slide, is 20% of the Keplerian rotation rate. It got to have in order to be able to form an accretion disk. There was another question, I know.
Maybe you discuss it, I don't understand, because my English is not very good. In this picture, the total energy
Yes.
during the plant may be proportional to mass of this layer.
Correct.
But really we see some events after the DRB which energy more than during the prompt or very, you understand?
I totally understand your
The
question.
energy,
I understand. Let me address. Yeah, I totally understand. I'm just going to rephrase what you said so that everybody, if in case somebody missed it, the question that is being asked is that there are bursts where the amount of energy that is seen to come out after the prompt phase is larger than the energy coming out in the prompt phase, and it could be as large as 10 times the energy, 10 times more energy coming out during this phase than it was during this phase. That's your question. That is the question that is being asked. And answer is that simply means that yes, if this model is correct, it simply means yes, there is more accretion during this phase than it was during this phase. Either that or the efficiency at which the accretion was converted to the outflow, the jet, relativistic jet, is more efficient here than it was during this. It's one or the two, or could be combination of the two together. Anything else? Then moving on.
Are you assuming there's a magnetic field here?
No magnetic field was assumed, at least in the accretion scenario. There would be magnetic field, but it would be generated. It would be generated by some instability in the disk. It could be, one of those magneto-rotational instability that has produced magnetic field, which in turn, for instance, will couple with the black hole to channel this outflow. So those are all there, certainly, and part of this picture. So I just wanted to share a couple of these interesting bursts. There are, in a sense, every burst is unique, but I wanted to highlight and point out two bursts. One burst, so-called naked eye burst, was at a redshift of about 1, and you could see it. You could see it with your naked eye, the optical flash, for about a minute. 5th magnitude. So if you knew where to look, if you were at the right location and so on. So this is unusual. This is just to give you a sense of the optical luminosity, several million times more luminous than the most luminous supernova in the optical band I'm talking about. So very, very luminous. Then, of course, redshift-wise, the highest redshift we have, we heard in the previous talk, is this particular burst, redshift of 9.4. Energy, not so much. Pretty typical energy for a GRB. And I will say more about it. In comparison with, so I have here 4 of the 5 cases of burst at redshift greater than 6. Information here, most of it you already saw in the previous lecture, but here the duration, this is the only one. And I mentioned that I will come back and share with you one burst with a duration of 225 seconds. But these other bursts, well, the typical duration is pretty typical of a long duration gamma ray burst. In our frame, of course, in the host galaxy rest frame, this one here is less than a second. The flux that we see is fairly typical. The amount of energy isotropic equivalent, something on the order of 10 to the 53. Nothing exceptional. If we look at the brightest Fermi burst, their isotropic equivalent of energy is approaching 10 to the 55 erg. So these are not exceptionally bright bursts. And so looking at, for instance, the Swift burst alert telescope sensitivity, gamma ray telescope sensitivity, which is here, compare that with the flux that we saw. This is, by the way, the average flux during the gamma ray flux during the prompt phase. So Swift can see bursts like these up to a redshift of 15. Of course, determining that they are at high redshift is very tricky matter. That's a totally different issue. But as far as detecting gamma ray emission, that's not a problem for Swift. And even better for this Chinese-French mission with a launch date not so clear, but maybe 2017, it has got more, it will be more sensitive than Swift, below 20 keV, and should be able to detect in principle higher redshift bursts in the X-ray gamma ray band. However, the follow-up observation that is being planned for this particular mission are several ground-based telescopes. 2, for instance, 2 infrared telescope, but only going out to highest wavelength is roughly 1 micron. These 2 telescopes located in Mexico and China, which means that they wouldn't be able to identify bursts beyond redshift of 8. The JANS mission is unfortunately not funded, so I'm not going to say anything more about it. So this is something that has already been talked about. I don't think that I'm going to add anything to it. So I'm just going to skip this particular slide and go to Fermi. This is also kind of talked about in the previous lecture. The only point that I wish to make slightly different from the spin of the lecture, the earlier lecture, is that if you look at gamma ray burst distribution with redshift and star formation here, this is the star formation rate, or co-moving volume of the universe as a function of redshift, gamma ray bursts seem really to fall off. Their number with redshift is falling off more slowly compared to star formation rate. Although there is a big error bar, certainly in the gamma ray burst statistic, that's a small number statistic, star formation also becomes very uncertain at a redshift more than about 3. So we do not know what that is, but based on this, it's possible that gamma ray bursts are falling off slower with redshift than star formation rate is.
This is correct, or it's the observed?
This, you mean the gamma ray rate? Gamma ray burst rate, not corrected for selection effects and so on. No, not corrected for selection. And that's another, of course, good point and worth certainly drawing attention to. What I want to do is say now physics. I'm not going to turn to physics as opposed to astronomy, and that is we have made good progress in understanding of gamma ray burst in the last 10 years. However, there are certain number of fundamental questions that remain unanswered. And I would like to highlight two, which in my mind are the two fundamental questions that are unanswered. One of which is whether a black hole or a neutron star is produced in these explosions. We don't know the answer to that. I will say a little bit more toward the very end. We do not know the composition of the relativistic jet that is produced in these explosions. Is it baryonic? Is it, for instance, electron-positron pairs? Is it magnetic? Is it pointing outflow? We don't know the answer to that. That's another fundamental question that remains unanswered. And to answer these questions, we would need to understand how gamma rays are produced and generated in these explosions, and then use that information to again invert and understand the working of the central engine and understand what the central engine is. So we need that information. This satellite, part of the purpose of this satellite was to try to understand how gamma rays are produced and understand the gamma ray prompt radiation mechanism. And there were surprises. There are two key results that Fermi found in regards to gamma ray burst. And those two results are here, shown here. One of which is that there is a delay between low energy and the high energy arrival time of photons. So photons of energy larger than 100 MeV, shown here in these last two panels, greater than 100 MeV, greater than 1 GeV, they arrive with a delay of a few seconds compared with lower energy photons. So that's discovery, one of the discovery. The other major discovery is that higher energy photons are seen, they last for a time much longer compared with lower energy MeV photons. So photons of hundreds of MeV last for something on the order of 1,000 seconds, and MeV emission, on the other hand, undergoes a sharp decline after tens of seconds, and certainly not seen for a period longer than half a minute. So those are the two big major discoveries of Fermi in regards to gamma ray burst. And let's try to see what does it teach us about the emission process, the mechanism, the physics of how photons are being produced. And I'm going to first talk about how high energy photons are produced, first give you an answer, then try to show you how we arrived at that answer. So how are gamma ray photons of energy greater than 100 MeV produced? The basic picture, I think, is very simple. That the jet, this is the relativistic jet produced in the produced by the central engine, whatever that might be, black hole or a neutron star. That jet starts to interact with the surrounding medium. It sends a strong shock wave into the surrounding medium, which transfers energy of the jet to the surrounding medium. The surrounding medium is heated up to very large temperature, and that in turn produces gamma rays via synchrotron process. That's the answer. Let me show you how we arrived at that answer. Some of you have seen this before, so my apologies, and probably many more of you have not seen this before. Here is the way we arrive at this, and here is kind of a proof, and I feel that it really is a proof that this is what is at work. This is emission, Fermi LAT, which stands for Large Area Telescope. That's the high energy instrument aboard Fermi. And this is the lower energy GBM instrument, which is sensitive to less than about 20 MeV light curve for one particular burst here. So my claim is, what I'm trying to convince you is that these photons that you see here are produced by synchrotron process in the external shock going into the external medium. Now this shock, like any other shock, is a self-similar solution. It's a self-similar thing. It's like Sadow-Taylor. It's the relativistic analog of the Sadow-Taylor solution. And in that case, it's very predictive. You can take, for instance, if this is coming from the shock at early time, then you should follow a very definite relationship between the frequency and the temporal decay, meaning the spectrum and the temporal decay are very well correlated. And there is a certain relationship between the temporal decay index alpha and the spectral decay index beta. They should satisfy this particular relationship if it is shock. And lo and behold, it satisfies this relationship exactly. This is precisely satisfied, but it's more than that. So if it is shock, then the shock as it is propagating is sweeping up more and more interstellar medium. The shock slows down. Okay? So it starts out with a Lorentz factor of few hundred. With time, the Lorentz factor is decreasing with time, and it will produce radiation, again synchrotron radiation, of longer wavelength, lower energy. So one can predict this self-similar shock wave at a later time. So see, here we are talking about 1,000 seconds or less. Then we can predict what it should do at later time, 100,000 seconds, which by the way is a day to several weeks. What should it do? What kind of emission should it produce in the optical band and in the X-ray band? So if I claim that 100 MeV photons are being produced by the shock and the synchrotron process, here is the prediction. The prediction gives you that this is where the X-ray should lie, this is where the optical flux should lie. Let's look at the data. Part of the data, certainly here, comes from Greiner and his group. And so this is the data, X-ray band data, optical band data. You can see for yourself, it's perfectly in agreement with the expectation of the shock. You can run this movie backward, pretend that Fermi never saw this burst, never saw the high energy emission in the 100 MeV. Pretend that you only had data from Greiner, X-ray and the optical. So this is shown here. You have X-ray data, you have optical data from this burst at late time, a day onward. That everybody, I think almost everybody in the community would agree that that emission is synchrotron radiation in the external shock. Okay? So now you can do a backward analysis. Say, okay, if that is the case, then what should the prediction be for 100 MeV emission at early time? And this is the prediction. So if this is external shock and synchrotron, this is what is predicted at 100 MeV at early time. So remember, we are going from 1 keV to 100 MeV. You are going from a day to minutes an hour. This is the prediction. And let's just see what Fermi saw. Well, here. So again, it's in very good agreement. So I would say that this is about as good of a proof, I think, as it gets that 100 MeV photon, certainly after the prompt phase, which means the first 30 seconds, maybe something else is going on. But from 30 seconds to 1,000 seconds, hundreds of MeV photons that Fermi LAT saw are synchrotron photons produced in the external shock, in the external medium. The other big thing is that if it is synchrotron, then you need magnetic field. You need energetic electrons. Electrons are moving with a Lorentz factor, for instance, in this case, about several million or maybe closer to 100 million Lorentz factor and magnetic field. Two things you need. Electrons are accelerated by Fermi process in shocks, not a problem. Magnetic field, I'm going to discuss that, but before that, let's take questions. Please go ahead.
Can you return?
Of course, let's go back. Here?
And I understand you. You say that the hard gamma ray emission is really non-prompt emission are light to afterglow emission in
Correct.
low shock, for
Correct.
example. In this case, I don't understand exactly how you can explain the very complicated structure of the initial stage of hard emission. This first question.
Good.
The next questions, if we come back to short GRB,
Yes.
we cannot find any matter around in this case, and but we see a hard emission.
Good. Good. Let me address both questions. Very good. You know, I understand both questions. Let me address that. Question number one, the point is that high variability that is seen during the prompt is not going to be produced by the shock. Very correct. That's why I was very careful to say that the emission that we see during the first 30 seconds, which is the prompt phase, something else is going on. And 30 second onward, from 30 second to about 1,000 second, this is what's going on, which is the shock in the external medium and synchrotron radiation. But the first 30 second remains a mystery, and that is a mystery I'm going to come in like just 2-3 slides. I'm going to come to that mystery. So I totally am with you that it does not explain the first 30 seconds. The second question that you asked, the second question about the short burst. Now, it's impossible not to have any material. The difference between the short burst and the long burst is quantitative. What's the density of the medium in the vicinity of these explosions? In the short burst, which are going off at larger distance from the centers of galaxies, by the way, that's not always true. There is a big distribution in the distance, correct? Okay, right. So, but some short bursts are there which are going off at a distance of 5 kiloparsec, maybe 10 kiloparsec from the center of the galaxy. The density is low, but non-zero. The density is something on the order of maybe 10 to the power minus 3 particle per cc, as opposed to 1 particle per cc. And shocks are produced just at a slightly larger distances.
No, I don't agree with you, because before the collision
Yes.
starts,
Yes.
we have the sun envelope around the binary stars due to the electromagnetic emission of the binary neutron stars.
Good.
If they do two neutrons, we see such envelope around the pulsar.
Good. Good. No, I know.
And dimension about 0.1%.
Yes.
It's very large.
What?
No matter, no gas, only the relativistical part.
Yes. Look. So part of what you're saying, you are actually answering your own question, which is that there is a non-zero density of matter in the vicinity of pulsars, neutron star, and all this afterglow that you see.
I understand your point.
Okay. There is another question here.
Maybe discussion.
Certainly. There was another question here.
Been answered.
It's been answered. All right. Certainly.
Since we spent so long on this, the spectrum at 100 MeV is much flatter than it is by the time you put the X-rays. I assume that means the electron spectrum is steepening, but it doesn't seem to steepen when you get to the optical.
Actually, there is not that difference between 100 MeV spectrum and the X-ray spectrum. This is looking at the time. This is looking at the time, right?
Looking at the red, it looks fairly flat.
You mean in the terms of the temporal decay?
Yeah.
Temporal decay behavior, by the way, temporal decay behavior, yes, but very slight differences there. But yes, correct. So, this is because of the fact, the thought that you had, and I don't want to jump your thought, you are saying that is because of the fact that in the high energy band, you kind of switched the spectral regime. That's probably what you are saying. And that's certainly true. Am I misreading your question?
I'm guessing that.
That was your guess, and that is correct. Several other questions. Let's take. I saw you first.
Okay.
So,
In your model, when the X-ray after row starts,
X-ray would be always present, even from the very earliest time.
observable by GBM.
Very good question. So GBM, yes, it is not. That was also your question. Very good. So here it is not shown. But if I were to show, for instance, on the same graph, I have one of the graphs later on, which I can share. But let me answer the question. So X-ray will be well below the GBM. So X-ray from the external shock will be well below the GBM. band. So we have clearly, that's a good obvious question. We have certainly looked at it, and that's the answer. Any other question before I go on to the next, almost the next last part of, how am I doing? Not so good, which means I have to make a decision here. I have to make a decision, we have to make a decision collectively. I could stop. I mean, technically I have used up 45 minutes.
No. You should
No, I
have,
think it's good because we're
You
in
should
the
have 10
discussion
minutes.
section.
Okay,
you should have 10 minutes.
I have what?
10 minutes.
I have 10 minutes. Oh, okay,
Go ahead.
all right. The question that I was going to address is how magnetic field is generated. You need magnetic field for synchrotron radiation. And what I want to share with you here is that that's a big problem no matter where in astrophysics you ask that question, how magnetic field is generated. In case of gamma ray burst, particularly the Fermi burst detected by Fermi, I'm providing a very simple answer. And that answer is that in this case, magnetic field is generated, it's a weak magnetic field. Something on the order of milligauss magnetic field. Tens of milligauss magnetic field is all that you need to produce synchrotron even at hundreds of MeV. And second, what I'm saying is that that magnetic field is really the interstellar magnetic field which is compressed by the shock. The blast wave which is moving with a Lorentz factor of few hundred, that interstellar magnetic field is compressed and amplified, and that's sufficient to produce the synchrotron emission that we see or Fermi saw at hundreds of MeV. That's the answer that is being provided here in these slides. The technical details you can always ask me, and I'll be happy to go over that. And the answer seems entirely consistent. No matter whether you take the early LAT data of few hundred seconds to 1,000 seconds, or you take, for instance, the late time, 1 day data in the optical and the X-ray band, they provide an entirely self-consistent picture about the generation of magnetic field. There is more information, unpublished, and that is coming from my student, Rodolfo Santana. He has looked at a bunch of bursts detected by Fermi. In this case, I'm showing 35 bursts and showing what the magnetic field distribution is, parameterized in the terms of so-called epsilon B parameter, which simply says what fraction of the shock plasma energy is going into magnetic field. And the answer seems to be typically fairly small, something on the order of 10 to the power minus 5 of the energy of the shock wave is going into magnetic field. So it only requires mild amplification. Amplification by a factor of maybe 10, 20, not by a factor of certainly tens of thousands. That appears not to be needed in the case of gamma ray burst. The question that was asked, and now I come back to it, I promise that I will come back to it, how is the emission produced at earlier time during the prompt phase and at lower photon energies of MeV? And that physics remains highly uncertain and highly controversial. And we need to understand that because this is the emission which carries a good fraction of the energy of the explosion, and this is our best way to understand the central engine, whether it's black hole, neutron star, whatever it is, that offers the best hope. So we do need to understand how these MeV photons are being produced during the first half a minute or so. And there are lots of people who have worked on it. This is by no means a complete list of everyone, but this is a selection of papers to give you a flavor of the number of man-years of work that has gone into trying to understand this radiation process. There are a wide variety of proposals. It could be synchrotron, inverse Compton, synchrotron self-Compton, etc., etc., etc. Many, many mechanisms. And let me just share with you what I advertised, that the current paradigm that we have is not working. I think I can go a little further than that, and I say that the current paradigm, in my opinion, is ruled out. And the current paradigm is that gamma rays of MeV energy are produced in the so-called internal shock, which means shocks not in the external medium, but shock within the jet itself. That internal shock paradigm, I think, is not correct. It's not working. It's in conflict with the data. There are many, many things. I could give you an hour-long lecture on this alone, but let me summarize in one single slide. The problem is that it produces the wrong spectrum. The spectrum is too soft. The low energy spectral slope should be nu minus half, and that's not consistent with the excellent data that we have from numerous satellites. And the other possibility is the emission could be internal shock and synchrotron self-Compton. If that were the case, it should give rise to very bright optical flash associated with the gamma ray. And we see that occasionally, but occasionally, very few cases. Many more cases we have got good limits, and that suggests that SSC is most likely not at work. What may be going on? There are three possibilities. One of which is that we have, for instance, thermal emission, which is inverse Compton is scattered multiple times. That could be a possibility. The only trouble is that there are not very many bursts where we see actually thermal spectrum. There are few cases where we do, but many more cases where we do not see thermal spectrum. So that's the problem. There could be, for instance, electrons are being continuously accelerated, such as, not in shocks, but such as, for instance, magnetic jet, magnetic outflow. So that could be a possible solution. And it could be that we have got a turbulence, relativistic turbulence within the jet itself. How that is produced, uncertain, but it could be a result of magnetic reconnection in a magnetic outflow. Those are the possible solutions. And I'm coming to the very, very end. In the last minute or two, I just want to share with you, again, some of you have seen this cartoon version of the suggestion that you have got turbulence within this jet where there are outflow within the jet moving with a Lorentz factor of maybe a few to 10. Therefore, you see, so to speak, only small patches of the jet moving in your direction, which could be responsible for the rapid variability that we see during the prompt phase. So that could be a possibility. Other big question, is it a black hole at the center or is it a magnetar? We don't know the answer to it. How are we going to find out the answer to it? Well, it is going to come from the data. So one of the discoveries of Swift is that the X-ray light curve after the prompt phase is declining as 1 over t cubed. We can ask, what's the expectation for a magnetar? The most natural expectation of a magnetar model is that the luminosity should decline as 1 over t squared. If it is magnetic dipole radiation, you can easily show that that's the behavior that you expect. However, the breaking index of pulsars is not 3, but it is flatter than 3. That could give you a little steeper light curve. So that remains unclear. Some bursts, and that is disputed, but there seem to be some bursts which have energy corrected for the beaming is still exceeding 10 to the 52 erg. If it is magnetar, the energy that is being tapped into is the rotational energy of a neutron star which is spinning with millisecond period. So the total energy reservoir is a few times 10 to the 52 erg, and when you see energy exceeding that, you know that something else is going on. And as I say, that is controversial, but it may be that that's another way that we can pin down what's there at the center, black hole versus magnetar. So what's the best way that we can determine the composition of the jet and black hole versus neutron star? Clearly, optical infrared observation at early time on time scales of tens of seconds will help tremendously, because we would be able to figure out whether the jet material is baryonic or non-baryonic. And it needs about a factor of 10 sensitivity improvement in the optical infrared on less than certainly about a minute to be able to do that. Ice cube result provide constraint, but they are not quite there yet to be able to really constant the jet composition. So that's it. I'm just going to maybe even leave this summary slide here and take questions. This is what we have learned about gamma ray burst. This is a summary of it. Here are the big open questions. So I'll just leave it at that. And let's take questions.